Good morning, class. This week we're going to be talking about convolutional neural networks and transfer learning. Now, as you know, computer vision is one of the subfields or the areas that really caused the deep neural networks to become popular. And let's go over a few of the tasks that are very popular in this field. We have image classification. In this case, we're just going to be classifying, does this image contain a chair or not? Then we could also do not just classifying the fact that it has a chair, but also localizing the chair. In this case, we can draw a box around the chair. One step further would be object detection, whereby we're sort of drawing boxes or detecting where the objects are in a certain image. A lot more fine-tuned even is image segmentation, whereby we're going to predict exactly where is the chair in the last image here. So in order to predict that, what we're basically predicting is something called a mask. A mask would be, in this case, a transparent image whereby only the blue is 1 and the rest is predicted as 0. All right, now when we're doing these tasks in image detection, we actually have a lot of challenges. In this case, when we're trying to get some data from a satellite image, is this a satellite? A very zoomed in satellite image, there may be background clutter, some things lying around that really detract from what you're trying to predict. Maybe you're trying to detect cars, but some of this clutter might seem like cars or not. Images might be occluded. There might be trees covering the highway. There may be variation in objects, so there's maybe shades over them. There may be different kinds and colors of cars, etc. So these are all challenges that we're going to have to deal with when we're doing object detection. Okay. This is a slide I got from an NVIDIA workshop that I gave once, and it basically reiterates the fact that deep learning with convolutional neural networks really is everywhere in our daily lives. It's becoming ever more apparent, right? If we're moving towards a society in which autonomous vehicles are becoming a thing, obviously autonomous vehicles or AVs have a lot of object detection going in. They have lane recognition, they're recognizing traffic signs, traffic lights, etc. But it actually goes to more hidden layers of our society. Obviously in Singapore, it's quite clear that there is some surveillance going on. So any place which has CCTV, the camera network around the city, they will be doing object recognition, crowd detection, all sorts of things to ensure the safety of society. In media, obviously we'll be having things such as, in entertainment, we have things like we want to be able to search videos for certain things. Maybe you want to search for action movies. In this case, a machine learning algorithm inside of Netflix might detect which movies have a lot of action scenes and then suggest similar movies based on this. Okay. Video captioning just means sort of describing in text form what happens within a video. In biology, there's a lot going on with medical imaging. So MRI images, so this is microscope images for cancer cell detection, etc. I believe there's also a COVID-related challenge out right now in which X-rays of lungs are made available to detect if it's COVID or a normal pneumonia. Then there's of course the internet and everything that happens within it. So people are doing sentiment analysis in real time. Like there's little softwares you can install, and my research group works on this as well, whereby you look at a face, you can see if it's smiling or not. This is very useful to do some recommendation things, for instance. Okay. So we can also classify images for all sorts of purposes. Maybe you want to do some sort of detection, what is on a website, what is on a YouTube video, so that you can then propose correct advertising. Okay. Speech recognition is in there too. Why is that? Because speech is often Speech is often represented either as an image, as a spectrogram image, or as a 1D vector, a waveform. And that 1D vector we can actually also perform convolution on. Okay, so in this case, one-dimensional convolution. I put some other pictures. For instance, here we have the OpenPose software. That would be this one here, whereby you install it. It's pretty cool, and it detects your skeleton in real time. You don't need a Kinect infrared camera for this. It just does it based on images. So that can be very useful for game applications, etc. There's also some work on using CNNs for predicting the morphological parameters of galaxies. This is important to study their formation and evolution. So this would be based on the images you see here. The images above, they represent, I believe, they are tumor images, right? So in this case, we're detecting if they're benign or not. Others include, we have some game examples here. Using an image of a game, we can use reinforcement learning with convolutional neural networks to predict what action the game bot should take to defeat you. Convolutional neural networks were first conceived by Jan LeCun, who's now chief scientist at Facebook. Remember, LeCun is one of the 3 big names in machine learning. Convolutional neural networks are basically a special type of neural network that process data in a grid-like topology. Now, it can be 2-dimensional grid, it can be 1-dimensional, 3-dimensional, or even higher dimensional. So some examples are time series data, 1-dimensional. Images, very popular, 2-dimensional. There's also point clouds, 3-dimensional, etc. The name convolutional neural network comes from the fact that it employs a convolution operation. So it's a mathematical operation. And the advantage of convolutional neural networks is that because of this convolution operator, things can be calculated as matrix operations that can be processed on the GPU very quickly. And the way that the neural network is organized with the filter, etc., as we'll see in a little bit, makes it very efficient to be executed. So basically a CNN is very much like neural network, except instead of fully connected layers, as we call them, or dense layers, we now have a CNN, or a convolutional layer, one or multiple convolutional layers. So it works in the same way. You feed it an input image to the network, and you'll get an output label. Perhaps if you're classifying objects, you want to have an image class. So as an example, we could feed it a happy face, a sad face, and we predict if the face is happy or sad. Quite basic. Now images, if we have a little bit of a deeper look at images, they're basically numbers. If you know color theory a little bit, you know that we use 3 channels of colors, okay, red, green, and blue. Your screen, your computer screen for instance, will consist of 3, each pixel will have 3 different lights, a red, green, and a blue, and the intensity of each of these colors combined will form your final color. The way this is stored inside the image is in 3 layers, 1 layer for each color. So we have, we have a layer for red, green, and blue. Okay. And within each layer, we have basically the image as a matrix, and for each pixel, we'll have a value, which is the intensity of that particular color. Now, to simplify, in the examples that follow, we're going to be using just a black and white image, not a grayscale image, but black and white. That means that the pixels are either 0 or 1. Using 0 or 1 translates in images that look like this, of course without the grid. So, why do we use convolution? Now let's look back at the color image. 24-bit color image, which is what we call these days true color. This means that 24 divided by 3, we have 8 bits per color. 8-bit could be 0 to 255, so 256 values. So for each layer, we can multiply the number of bits that we have, meaning that we have this many combinations of colors. Okay. So when we feed these color images, each of these channels into our neural network, usually we'll normalize the value between 0 and 1, which will increase the performance of our network quite a bit. Okay. How does convolution work? Let's go through an example step by step. First of all, imagine that we'd have a 300 by 300 image. Okay, this is the resolution. 300 by 300 is quite low. Okay. That means we have 3 channels, so our input equals 300 by 300 by 3 channels for each color. 270k values as input. Okay. Now if we'd have only 1,000 values in a normal fully connected layer, so we're not using convolution here, then that would equate, because it's fully connected, so I mean each of the 270k inputs is connected to each of the fully connected layer. That means we'd have 270 million, yes, million weights for us to train only in the first layer. So that's immense for a small 300 by 300 image. Okay. So if we have a network like that, it is infeasible to train, especially if it gets deeper. There's a super high chance of overfitting because you have a highly complex network with many, many, many parameters. Okay. So the solution for this is convolution. It drastically reduces the number of parameters that we need to learn. Okay. Plus, it preserves locality. Because of this mechanism that we'll see in a little bit called filters, we don't have to flatten the image to a matrix. So what we did here, the image gets flattened into a vector. Instead, in convolution, we keep our image in 2D form. That means that relationships, vertical relationships, for instance, can be kept. Yeah. Typically, a convolutional neural network will take in the images. It will have the actual CNN classifier, and then it'll give you the class predictions. Within this classifier, the central area here, we have a convolution layer plus an activation, as standard is. So in this case, the dense layer, the fully connected layer, is just replaced with the convolution layer. Then we do an operation called pooling. More on how that works in a little bit. We repeat the whole thing, repeat it. Then, because we're still working with a 2D image with multiple channels, which is kind of 3D, then we flatten it. We feed it into normal neural networks to get a final end prediction. If we're doing classification, typically using softmax. Okay. We're going to go over each of these elements of this drawing in detail. Alright, so we start from a black and white image, just as an example. We take one channel here, and we go over a convolutional layer. Okay. So we'll have one input image, and we'll have many feature maps as output after one convolutional layer. The amount of feature maps we have is equal to the amount of filters that we have. Okay. When we do convolution, we actually use a mathematical, well, you might think that we use the mathematical operation for convolution, which is a sort of a special type of matrix multiplication. In the discrete case, if it's a continuous version, we can also write it as in the discrete as a continuous version, but then we basically just take the integrals. But there is a catch here. We're not really using convolution. What we're actually using is a cross correlation. Okay. There's a small difference here. Notice the sign, okay, which changes the way we do the operations. Okay. I give you these equations and have a good look at them, because we're going to be doing the actual matrix multiplications in the next slide. So then you can revert back to better understand these equations. Okay. So what's the difference between cross-correlation? There's actually not much difference. The only thing that happens because of this sign change is that the filters that we use, the filters are actually the weights that we train, will be transposed. Okay. So it's important to know that, well, it's nice to know that when we use a cross-correlation operation, we actually do the same thing as convolution, except that the resulting kernels that we learn are transposed. Now, why don't we just use convolution? Because convolution actually is mathematically more complex. Okay, so especially the flipping operation that occurs during inference actually causes a bit of a slowdown. So why not take the quicker operation, cross-correlation, and then just realize that the filters are transposed. There's no need to actually transpose the filters back. No, we just have these filters because we're using cross-correlation. So this is sort of something that not too many people point out usually, but I thought it would be nice to know. All right, so convolution really is equivalent to flipping the filter. Let's see how this filter is flipped. Okay. If you have symmetrical kernels, both result in the same output. Okay, so in case my filter would be something like this. It wouldn't matter if we do cross-correlation or convolution. Okay, so typically machine learning libraries implement cross-correlation but actually call it convolution. Something to keep in mind. All right, now let's make this a bit more concrete. Let's take an image input here. Notice it's not normalized because it's easier to calculate with integers, but usually we would normalize this one. Okay. All right, so we have our input image, which is 6 by 6 matrix, and we have a filter, and we want to calculate the convolution of this. You can revert back to the formulas I gave you, but let's go through it. First, we have a sort of sliding window that we use to multiply with the filter. Okay. In the first case, we perform this convolution operation, and we multiply each element by each filter element. Okay, so 3 multiplied by 3 is 3 plus 1 multiplied by 1, 4 plus 2 multiplied by 1, 2, 0 multiplied by 0, 5 by 5, 7 by 7. I have the full operation here for you. It results in -5. Okay. That is the first step of your convolution. Then we are going to slide this window. Notice that we use a hop size of 1. We'll talk about that later. We slide the window and we calculate the next element. Same thing, 0 multiplied by 1, 5 multiplied by 1. See how this is a very quick and easy operation to execute. And we get our next element. Okay. We do this for each window while sliding, and we get our resulting, what we call feature vector or image map. If we have a real color image, we would have 3 channels of this, meaning 3 matrices like this. And for each of the channels, we'd get a different image feature. All right. What does this do? It's already listed. This particular filter does something called edge detection. It doesn't become apparent from this example. So let's take a closer look at a different example. This matrix here, how does this image look like? It looks, if we have our image here, it looks like this. Right. It's half dark, half white. So if we apply an edge detection filter to it, it should really highlight this area here. All right. Okay, so we do the same convolution. You can do the calculations 10 by 1, 10 times 1, okay, right, etc. And then multiply it by another. It actually equates to 0 because these zeros, these are minus 10s. Okay, so the first result is 0. If we shift our sliding window to here, we calculate it again. This time we get 30. Then we slide our window again, and again we get 30. The last window we get 0. So indeed what we want is what we see. The edge detection filter has highlighted the central area of the image. Alright, so as I mentioned, usually we have a few channels in our image, and it would have a certain dimensions. So for instance 32 by 32. When we convolve is what we call it, when we do this convolution operation using a filter typically also has a number of channels, we get something called a feature map or an activation map. Okay. Each filter creates an activation map. So that means if we have multiple filters, we're gonna be getting multiple activation maps or feature maps. Then we end up with a stack of images. In this case, we have 6 filters, we get 6 feature maps. So we get a new image. In this case, it's almost bigger. Right? The resolution is a bit lower, 28 by 28 instead of 32, but we have 6 feature maps. Right, so a convnet, a convolutional net, is a sequence of convolutional layers, usually interspersed with activation functions. So very much like neural networks, we have layers and activations. Popular activation is a ReLU activation. If you remember, looks like this. It's 0 when x is smaller than 0, and it's very linear, x equals y afterwards. Alright, so at each time, when you have 6 filters, you get 6 feature maps, then you have 10 filters, you get 10 feature maps, etc. And we notice a small decline in the resolution each time. I'll talk more about that in a second. Okay, so here we see a nice GIF animation of how a filter is being applied. This is the first filter. This is a second filter, creates a second feature map, and so on and so on. Okay, so you see the filter has 3 channels here too. All right. So if we have these conv nets that become deeper, we actually see that they learn different types of features. We have a network here again. We start from an input. We have our first layer, deeper and deeper. We see that first we find very low-level features, such as the one we just saw, an edge detection. All sorts of edge detectors. When we go deeper into the neural network, we find more and more meaningful features. So this is a very cool feature of convolutional neural network. We can see facial features, eyes, noses being formed. And at the very end of the neural network, we'll even see high-level features such as forms and shapes of faces. So this is one of the very cool things. I put a web link here for those of you who are interested. This is an online site where you can feed in an image and apply different types of filters to see what the effect is on the actual image, which is pretty cool. In fact, we can have a little look at it. Okay, have a look here. This would be we can have an edge filter, for instance, on this image, apply the filter, and you see how the edges are highlighted. Okay. What else can we do? We can have a sharpen filter. This is how it looks like. Apply it, and it sharpens the image. Interesting. Right. So let's have a closer look at these dimensions, because we noticed that the dimension of the image decreased at each step. Suppose we have a 7x7 input with a 3x3 filter. We slide our window like this. So we slide it 4 times horizontally, then we skip to the next row and we do it again. So that means in total, because we slide it 4 times plus the original time, we have a 5x5 output after convolution. Okay. Now, if we have a stride of 2, like a hop size of 2, that means we don't do this one. We immediately go to the next one. Then our output will be smaller. We'll have a 3x3 output. What if we have stride 3? What is the output size? Okay, so we start here. This is our first window. We shift it 1, 2, 3 to here. It actually causes a conflict. It doesn't work very well. All right. So you would have a final output of 2.33. That doesn't work. Okay. We can calculate it by hand like we had earlier, but there's actually a little formula you can use to calculate. We have the input size 7 minus the filter size, let's say 2 in the previous example, divided by the stride size plus 1, and it will give you the calculated resulting output sizes. Okay. If you calculate this, this will give you an error. Okay, won't work. You can't use stride size 3. But what if you really do want to? Okay. The answer is use padding. Okay. In fact, padding is often used so you don't lose you don't diminish the dimension of your image. If we use a padding of 1, that means we add a row and column of zeros around our original input image. In this case, we have a 1 pixel border, and if we apply a 3x3 filter to the 7x7 output, now we have, sorry, not a 7x7 output, we will have a 3x3 output. Because we can do a filter here. First one, the second one shifted by 3 here, and then the third one shifted by 3 again, like this. So we have 3 windows per row. Okay. So output is 3x3. In general, it's very common to see convolutional layers with stride 1 and filters of size f by f. Typically, the filters are kept pretty small, okay, and 0 padding, okay, calculated by f minus 1 divided by 2. This will preserve the size spatially, so it means your dimensions of your input image will not shrink. All right, let's have another example. 7x7 input again, 3x3 filter as we're used to. Oops. And we feed it. All right, so what happens after convolution? We've discussed how this part of this drawing works. What happens next? Well, we typically have a nonlinear activation. Okay, again, we want to make this simple matrix operation nonlinear, so that we're able to model more complex things. So we can use hyperbolic tangent, sigmoid, radioactivation, or other. The most popular, which often seems to perform best, would be ReLU. Again, I drew it here. We've discussed this already. Now, we really want our neural network to be non-linear. This is the whole point of using something as complex as neural networks, because then we're able to capture real-world data. Okay. So after each convolutional neural layer, we apply an activation layer immediately. Okay. After this, if you recall this drawing, we did activation. Now we're going to pooling. Now pooling is a specialized operation typical for convolutional neural networks. And it's actually a nonlinear downsampling, which makes the output more simple. Okay, so it reduces the size of the representation. So then means we can speed up the computation, as well as make some of the features more robust and less overfitting. Very popular type of pooling would be max pooling and average pooling. Often the pooling is of shape 2 by 2, sometimes 4 by 4. But if the window gets too large, you really lose a lot of information. Typically, non-overlapping windows perform the best. So that means if your pooling is 4 by 4, your stride length is also 4. It's non-overlapping. Here's an example. If we do max pooling, that means we have a 2 by 2 pooling here. We start in a window, we take the maximum element, 20 here. Then the next window here, we take the max element, 30. Then here the maximum element would be 112, then 37. Okay. So that forms our final maximum pooling output. If we do average pooling, quite logical, we take the average of the window. Okay, in this case, the first window, 12 plus 20 plus 8 plus 12 is 52 divided by 4 should be 13. Okay. So pooling layers don't learn anything about the features, they just reduce the size of a problem. You can think of it as a sort of smoothing. Okay. After our convolutional ReLU or activation and then pooling, we then do a flattening if we're done with all the convolutions. Okay, so this we could do the convolutions a few times. Let's go back to the image. Convolution, convolution, and then when we're ready to go back to normal neural networks, we do a flattening. If we flatten, quite easily, it's just a reshaping of the tensor. Then we get to fully connected layers. Now, fully connected layers, we're back into the class of last week. We do the high-level reasoning of the neural network. Okay, so because they have connections to all activations in the previous layer, they can again be computed as a simple matrix multiplication. Okay, so a point-by-point multiplication. Linear combination, again followed by an activation layer, a non-linear activation layer. And finally, we have a loss that we add at the end of the fully connected layers when we're training our network as a whole, so both the convolutional layers as the fully connected layers. In fact, in the convolutional layers, what we're trying to train is what the filters look like. The filters here are our weights. Okay, so as a training loss, again, we use softmax for multi-class classification, sigmoid cross-entropy loss for binary classification, and some mean squared error loss for regression. Okay. Very similar to last week. All right, softmax, for instance, if we are trying to classify between dog and cat images here, for instance, we have our CNNs here first, then finally our network is flattened, we have some fully connected layers. The example has two because it's traditional, one of the first introduced neural network, convolutional neural networks, but it can be any configuration you want. And the softmax, again with this formula that I showed last class, will give us the probability for each of the classes. Note that they summarize to 1 in total. All right, How does it look in PyTorch? Okay. Again, we use the module class to define our neural network. In this case, we have two convolutional neural networks. It's 2D because they're images, so we call NN2D. It has one input channel, black and white image. It has 6 output channels here and a kernel size of 5. Okay. Second convolutional layer is defined here. Then finally, we have one linear layer as the output. Then we sort of put everything together in a forward pass. We do convolutional one that we defined here, 2D convolution, followed by ReLU and max pooling. Again, convolutional 2D, max pooling, and then finally we flatten it. So we can use the view command. You remember from the first lab, we used the view command to flatten layers. Using -1 puts everything in one column or one row. Finally, in the last linear layer, we perform fully connected layer and return that output. We define a criterion, cross entropy loss, which already includes softmax, by the way, as our final output layer. We'll look at an example of this in the lab. All right, so that is sort of a summary of how convolutional neural networks work. Things will become more clear in the lab when we see examples, but the basic principle is fairly simple. But let's talk about a concept that's actually very important in increasing your performance, not just in the convolutional neural network domain, but also for language or text processing. Okay, which is called transfer learning. Transfer learning basically takes a trained network or feature extractor from one task and applies it to a different task. Okay, so it's a sort of optimization, a shortcut that saves you time in getting better performance. Typically, you will start with a higher performance and maybe even end up with a higher performance. Okay, but I must say that it's not a given that your transferred knowledge will increase your performance until after your model has been developed and evaluated. So it is important to still evaluate your increase in performance or not. Okay. So possible benefits include a higher start in performance, a higher slope, quicker improvement, and a higher asymptote. So it's converged to a higher level. So ideally, we see all 3 of these benefits. Okay. So to get this, we can try to identify a task that has lots and lots of data, that maybe already has a trained model on it, especially for that data, and that you could sort of use this pre-trained model for your own problem. Okay. This becomes especially relevant if you're dealing with a task that has almost no data available, yet somebody else has used it on something that has lots of data available. Okay. A very typical example here is object detection. Okay. There's data sets available there of millions of images classified. Let's take an example. Okay, if you have a huge data set of faces that have been classified to identify the speaker, and there's a data set that has millions and millions of faces, there's a model that's trained on it, it works very well. Now you have a problem, and your problem is maybe you have a very small data set, and you need to identify if there is a person in the frame or a dog. You can leverage the fact that there is a data set specialized on extracting facial features and use it for your problem. This is still very related problems, but it gives you an idea of the fact that pre-trained feature extractors can be useful. Now, what we typically do in transfer learning is we still allow this network so this first part of your network that you're reusing from a different domain, you allow it to be fine-tuned and tailored to your problem that you're learning. So basically, what is it? We're not reinventing the wheel. We can use pre-trained models from I'm not sure what that's supposed to be. We can use pre-trained models from an existing data set or task and use these to represent our inputs, then importantly, fine-tune their weights further. Okay. So remember here, we're not reinventing the wheel. In case of our lab last week, we used pre-trained, I think we used this one, the Word2Vec dataset pre-trained on the whole of Wikipedia from 2014. Using these existing word embeddings can help us with our network. Now, to be fully transfer learning, we should also allow this part of our network, this first one-layer neural network, to be further trained. In the case of Word2Vec, for instance, we should fine-tune these weights further, which we didn't do in the lab, to be fully considered transfer learning. Still, it gives us a head start to start from pre-trained neural networks. Okay. So back to images. Let's have a look at some famous pre-trained networks that are typically leveraged in transfer learning. The very first neural network, which was seen as a stride forward in the area of convolutional neural networks, was LeNet 5. 5 refers to the depth of the weight of the network. At that moment in time, 1998, was considered a very deep neural network. And basically it is this architecture that we've been looking at during the whole class. We have convolution layer. Subsampling is a type of average pooling with learnable weights per feature map. Fully connected, and some Gaussian output. Okay. So this neural network has 60,000 parameters, meaning we need to train 60,000 weights. Okay, that's not so bad. Okay. LeNet was first developed to work on the MNIST dataset. I think you're probably familiar with this one already. MNIST is a dataset of postal codes. They have handwritten numbers, and we need to classify from 0 to 9 which number is being written. Hence, the input is actually very small, 32 by 32. It's sort of the hello world of deep learning. So this dataset was first collected in an attempt to automate some of the sorting of postage in the US postal system. It performed very well, but then in 2012, which is 4 years later, AlexNet was born. AlexNet is an further extension of LeNet, and it consists this time of 7 hidden layers, and it was applied to the ImageNet competition. Okay. ImageNet has bigger images. ImageNet is a very famous competition. It has 1.2 million training images of 1,000 classes. Okay. It has object detection for 1,000 objects. This is a huge data set, and it's sort of the gold standard in the whole computer vision domain. By this first 7-layer neural network, the ImageNet competition made a huge stride forward in performance. Okay. And this particular entry to the competition made the whole computer vision community take a serious look at convolutional neural network, or deep learning for computer vision. And then this is around the area where deep learning started to become really popular. Okay. The resulting network has about 60 million weights to train, which is quite a lot. Then 2 years later, now people were getting really excited about the whole deep learning approach. The VGG network was introduced. It is, again, a lot deeper, 16 layers here, that's why we call it VGG 16. And it is a very homogeneous architecture that basically cuts the image in half at each convolutional layer. So you see the resolution goes in half very quickly. It is 7 layers. It uses 2x2 pooling from the beginning to the end, so at each layer, and it results in 138 parameters, 138 million parameters. Okay, so it's about 2-3 times as much as the previous one. Again, performs a lot better on the ImageNet competition. Then we go to the Inception Net developed by Google the Net, again same year, for this ImageNet competition. The model basically is comprised of a basic unit referred to as an inception cell that performs a series of convolutions at different scales and subsequently aggregates the result. So what does it do? The input is split up, you see it in the image of the right. We have the previous layer. We do 1x1 convolution, another 1x1 convolution, 3x3 max pooling, followed by convolution. So you have different strategies. And at the end, we concatenate the output of the different filters, and it aggregates the result. So this sort of inception cell we can find throughout the network. It's a very deep network as well. This one has 5 million parameters in version 1. Version 3 has 23 million parameters. So to this day, it's still very effective model. ResNet, very famous. We often refer to ResNet 50, still to this day, for object recognition. It's the winner of the ImageNet competition in 2015, and now we take a stride forward from neural networks that have tens of layers to neural networks that have hundreds of layers. Why is that? Because this network has something called a residual block. Normally, when we have a large number of layers in our network, after a while, we get something called a degradation problem. So, for instance, we have convolution, our representation becomes smaller and smaller. At a certain point, the optimal representation is learned for solving your, for instance, classification problem. So that means at that point, the next layers need to just copy the information. They don't need to do any complex operation, because at a certain point you found the optimal representation. You're just concerned with not losing this information. And this is what convolution neural networks can do. Okay? So because of the complex way this is calculated, we can't just learn to pass along the information. Okay? So this is where residual blocks come in. Residual blocks, basically what they do is they pass along information forward to other cells. Okay. This way, every now and then, when information was lost, we actually can look back to the original or the image map a few layers back. Okay. And this causes an amazing step in deep neural networks, because it allows us to go to way deeper layers, because every now and then we look back at less degraded or less further along inputs. Right, so this is a picture of what a ResNet would look like. Actually, it would be probably way bigger even. A plain network doesn't have these connections. So it does not look back, it doesn't have these residual blocks that look back at what the input was 2 layers back. So the resulting ResNet 50 has about 25 million parameters to learn, which is not that much given the amount of layers that we have. Okay, so this ImageNet competition, it really became interesting. This is I think it's the performance, so the error in terms of error. Before that, the error was pretty high. It all changes, so we have shallow neural networks here. Then we have AlexNet, which caused a really big performance increase, 8 layers. Then we have VGG-ish, another huge stride here, 19 layers. GoogleNet, the Inception network, ResNet, etc. Now our error is amazingly small. Okay. And if you look at, I should probably refresh the image here on the slides. If we look at current day results, are even better and better. So these ResNets, for instance, I use them in my research to do transfer learning for other tasks. So for instance, we use ResNet to capture objects, and we use these latent variables. So these halfway through the ResNet network, we use these variables to then feed them into an emotion detection network. All right, so here again, this error, there's a big difference here before and after people started using convolutional neural networks. This is the precision, the mean average precision of the image detection task. Okay, so what's next? We have ResNext, for instance, which is an extension of ResNet and basically replaces the standard residual block with something that leverages the split transform merge strategy that we saw in the Google Inception models. Okay, so instead of performing convolutionals over the input feature map, the block's input is projected onto a series of lower dimensional representation, of which we separately apply a few convolutional filters before merging the result. So we have this strategy like in Inception, whereby we split our results, lower dimensional, we do different type of filters, etc. And then there's also this residual block connection that gives us the original input, so we don't have a degradation problem. Finally, there's also DenseNet. Sorry. DenseNet, the idea is it might be useful to reference feature maps from earlier in the network. So thus, each layer's feature map is concatenated to the input of each successive layer. So it has a little bit similar to ResNet, but it looks back, as you see here, looks back to multiple layers and really far back in the past. Okay, so DenseNet can go up to 40 million parameters for this ImageNet competition, and it has an even better performance. So how does this work in PyTorch? We can very easily load an existing pre-trained model. For instance, we have our Inception model here. We set it pre-trained to be true. If you set it to false, then you just load the model architecture with randomly initialized weights. PyTorch also includes, for instance, ResNet 50 architectures and a ton of other ones. So once you have this model, you can use print here to see what the architecture looked like. I didn't have enough space here to put it on, but we'll try this out in the lab. Now, very interestingly, once you've loaded this model, you can actually change part of it. In this case, we call the model again, and then we say change the fully connected layer, so that will be the last layer of the model, and change it to a linear layer, same input as it had before. You could see that if you printed the model, and then you just change the number of output nodes to the amount of classes that you have in your dataset. So if you're doing cat-dog classification, but you're using the ResNet architecture, which has 1,000 different classes, you need to change that last layer so it outputs, so it looks at only 2 classes. Then you can start from this pre-trained model and fine-tune it to your dataset with a changed last layer. Okay. Right. So now let's have a deeper look at the MNIST application, which I already briefly mentioned before, which is basically the hello world of machine learning. MNIST looks like this. It is a handwritten number data set collected in the US Post Office, and it basically has, how much is it? Over 60,000 training examples and 10,000 test samples of different numbers that are handwritten. So there are 10 classes, 0 to 9. Jan LeCun used this dataset to create his LeNet 5. The images are very small, 28 by 28, and they are grayscale, meaning they have a pixel value from 0 to 255. If we train a simple LeNet, so 5 layers with 10 epochs. So an epoch means that we go through our entire dataset one time. So we train, so we feed the entire training dataset 10 times to the model in order to train it. Okay, so if we train on this architecture, we see an evolution of a loss function, much like we would expect to see. We see first the training loss, which is the blue line, goes down steeply in the beginning, then sort of stagnates. We have a validation set that we use to tweak the parameters, also goes down, slightly less, but still goes down. The accuracy obtained from the validation set is actually pretty high. So this is common. What we see, if the loss goes down, the accuracy goes up. So that's normal, that's what we expect to see. So first, we did a first experiment. We trained it on a very small data set, about 4 times less data as in the total data set. This allows us to just test our architecture and debug. So if you're developing something, it makes sense to train with less data so you can catch bugs, errors, without having to wait through the entire process. First result, we feed it a test image to, and it predicts the classes. The softmax gives us predictions for each of the classes. You remember the total is 1. Of course, there's a few missing classes here. And it tells us, indeed, it predicts 2 with 71% certainty. That's okay. Now, if we feed it a bunch of other testing images, these, then we see the prediction results. First 1, correct. First, then predicts 2, great. Here it predicts number 8. Predicts number 8 again, predicts 0, 8, correct. And 8, oh, it predicts correct, but very low certainty. Okay, so it's promising. So let's train on the full data set. Okay, so we have 60,000 images for training and 10,000 for test. If we look at the filters that we obtain here, some of these are depicted here, and we see that we have some diagonal edge detection going on, some features that might be part of, let's say this one. Does it look like it's a number, sort of a circle-like structure that could be used? There's some higher level features here that are useful when we're doing number detection. Okay, so we run this for 10 epochs. We achieve 99% accuracy. Great. We feed the same test set here. This is old results, this is the new results, and we see, oh, this is now wrong. This is correct, wrong, wrong, wrong. We predict 0 when we expect 7. It's correct. Actually, this is pretty bad result. So what happens? Do you have any idea why this gives a bad result? To understand this, we have to have a look at these test images and compare them with the original training dataset. If you recall, let's go back to the test dataset. All of the training images look like this: black background, white number. Okay. So that's what the model is being trained on. It has never seen images with different colors, images with different contrast, a dark background, for instance. So it's not going to perform well on that. Now, so what can we do to improve this? Okay, sorry. To improve this, we do a process called data augmentation. Okay. Maybe we can actually make our images look more like real-life images that we would imagine. Okay. So from our training set, one potential augmentation we can do is we can invert them. All black becomes white and all white becomes black. Now let's do that and see if the classification improves. So we invert the pixels, it's grayscale, so we use this little formula, and we double our training data set now with this as well. Now the results are super good, performs well, except this one is still a bit wonky. This is probably because the 8 here looks very different than the rest. It has this sort of separation and smiley faces in there, so we might have to do more augmentation to try to get it to work well for that. Anyway, a very big improvement just by doing a simple operation on our data set. So data augmentation and the way you feed your data to the system is extremely important. So there are much more operations that you can do. So you can also rotate images, shift, rescale, zoom, flip them, as you can see in the below example. Now in PyTorch is a very simple transform command that's depicted below that lets you do crop, resize, etc. All these operations very easily. Now, convolutional neural networks go way beyond images. As I mentioned in the introduction, anything that can be represented as a vector or a matrix, be it one-dimensional, two-dimensional, three-dimensional, and beyond, can be represented using convolutional neural networks. Think of video. Video is images, 2D, with a time dimension, which makes it 3D. Think of text processing, which is basically a text dimension. Think of word vectors, which can be used in a convolutional 1D convolution. Audio tasks as well. Audio tasks can be seen represented as spectrograms, which makes them images suited for 2D convolution, or they can be represented as waveforms. In this case, 1D convolution will be appropriate. So, in my research lab, we work on audio, music, and machine learning. If you're interested to have a look at the lab, we have weekly webinars that you can find on the website. So you're welcome to zoom in on that. So we work on topics such as music genre classification, audio transcription. If we have an MP3 file, can we detect which notes are being played? Spoofing detection. If you have a voice authorization system in your home, then could somebody record your voice and play it to the system to see if they can get access? So our spoofing detection system tries to detect these recording replay attacks. We also do hit song prediction. Does this audio signal have the potential to be a hit or not? Can we identify who is speaking? Can we detect emotion from music, voice, video, etc.? Now, how do we start some of this research? To properly understand that, let's have a look at some of the example images. All right, first of all, in its most basic form, image is a WAV file. We all know the old file type .wav. It's an uncompressed music file, so it's actually the highest quality that you can have. MP3s do some compressions on this signal. So waveforms are a bunch of numbers over time, which makes that they can be represented as the blue waveform above. So that can be directly fed into a convolutional neural network, and there's some very successful deep learning architectures at the moment that work with waveforms, such as WaveNet. However, a lot of the successful research uses spectrogram representation. In that case, you do Fourier analysis and basically decompose into frequency components. Okay. We get an image like here on the right, whereby our y-axis is the different frequency bins and our x-axis is time. Okay. So this shows that in the beginning there are some very low frequency components and a little bit more higher frequency components as we go along. Okay. Now, one particular type of spectrogram is what we call MEL spectrogram, and it seems to work very well with anything related to human hearing. Now, everything audio related is basically related to human hearing because we are always the ones listening to it. Now what a MEL spectrogram does is it rescales these frequency bins we have here to fit the range of a human hearing. So it makes the bins that we hear best a bit bigger. Okay, so MEL frequency spectrograms often perform very well when used as an input to any machine learning algorithm. Okay, if you're interested to do some work on using spectrograms as input for your project, for instance, you should check out NN Audio, which is my PhD students' PyTorch library, and it directly takes in the audio files and creates the spectrograms using GPU calculation as a first layer in PyTorch. Okay. So the mathematics are a little bit complex to go into, but the Fourier transformation, fast Fourier transform, basically can be represented as two kernel multiplications whereby he fixes the weights so that they become equivalent to this equation. And actually what's interesting is that if you calculate the spectrogram in this way using PyTorch, you can then let the weights be unfixed and train the perfect kernel for your particular problem. Okay, so if you're interested in that, check out the GitHub that Raven has made. It's very interesting. You just have an STFT layer, and it directly acts as a first layer in your network. Okay. It's also very easy to install. Just pip install NN Audio. Right, so in some other research, we do emotion prediction from both video and audio. In this paper linked here, we gathered a new data set consisting of music videos, but we also worked on an existing data set called Cognimuse, which is a data set of Hollywood movies. Now, we leveraged some pre-trained networks. So we leveraged ResNet 50 CNN to extract objects. We leveraged another pre-trained CNN to do scene detection, and then we used OpenSmile to extract a bunch of audio features. Okay, all of this was fed into an LSTM model, remember a sequence model, 2 LSTM layers, then a fully connected layer to do softmax prediction of 7 emotion classes. That works pretty well. The results are all described in the dataset, and what we found is actually very interesting. We noticed that if we train the model using only the audio features, it actually performs way better than if we train the model using only the video features, which sort of further justifies the idea that music and audio have a much stronger influence on our emotions than just video. Okay. Of course, when using both features together, we get the very best results. Now, we also use a convolutional neural network in one of my research projects on voice separation. So here what we're trying to do is we have a signal of music accompaniment and a voice singing, and we want to extract the voice from the music. This is useful, for instance, if we want to create a karaoke track. Okay. So when we do that, first let me show you an example of what the project is like, or what the data looks like. Here we have music with a singing voice. This is what we're trying to predict. Okay, so these two things is what we're trying to separate, the voice from the instrument. Right. How do we represent all this? Okay, so we use the masking technique. So we start from a spectrogram of the mixture, so meaning both accompaniment as well as singing voice. So this is what our data looks like. Mm-hmm. Then we give it labels, and the label would be where is the singing voice in the signal and where is it not. So we have this ground truth. So we can actually label parts of the spectrogram that are mostly highlighted in the singing voice. Okay. So then this sort of binary mask is what we're trying to predict. So just to recap what this binary mask is, this will be high or low depending on if the spectrogram is strongest at that, for that frequency bin at that point in time. If it's strongest for the singing voice, then for the accompaniment. So then it will be 0 or 1. So that is what we're trying to predict. We use a very deep convolutional neural network here. Input spectrogram, here CNN model, here we have spectrograms, convolution, max pooling, which you all know now, convolution, max pooling from dropout for regularization, flattening, fully connected, and finally sigmoid prediction. Now, why do you say sigmoid prediction? Aren't we predicting 0 or 1, which would be binary? No. We're actually predicting a soft mask. While we start from a binary mask, which is 0 or 1 as input, because we want to make a strong contrast, we're actually predicting continuous values. So it could be 9, 8. Right. So we're seeing this as a little bit of a regression problem for each of the output pixels. So once we predict our soft mask, or in case you're interested, our loss function here is cross entropy loss. Once we predicted that, we can then convolute our singing voice soft mask that we predict with the original mixture signal, mixture meaning both music and singing voice, and we get our final output spectrogram. Same we could do with the soft mask of the separated music accompaniment, which is the inverse of that one. So we know that automatically. And we get the mixture model. So what does that sound like? So not perfect, but no music in there. Great, no voice in there. Right. So this week in the lab, these were a few examples that we do in our research lab. If you're interested to learn more about this, check out my website. We have a bunch of examples there, and we do our weekly seminars as well. So this week in PyTorch, we're going to be doing image loading, data augmentation, some transfer learning as well, and I hope you will find it very interesting.
Go, Skylar, go!